Just a second. Okay, it seems everything works fine, surprisingly. Okay, welcome to our Tuesday seminar, seminars at the Warsaw University Astronomical Observatory. It's the last seminar this semester. Last but not least, we have Dr. Habilitated Agnieszka Slowikowska from Torun University, who's going to tell us about polarimetry in Piwnice. Just a few words. Agnieszka did her PhD in CET, then traveled the world, ended up in Zielona Góra, and then moved to Torun 3 years ago. And she is an active instrument builder and scientist working in a niche topic, which is polarimetry. And I hope we will learn more about it from Agnieszka. Please.
Good afternoon, everyone. Łukasz, thank you for the invitation. Today, I'm going to shortly discuss few scientific aspects of polarimetry, as well as development on hardware that we are performing now in Piwnice. And I hope to introduce to you a few instruments that we have here and maybe encourage you to use it. Just to be quick regarding polarimetry, which are described the best, well, the most useful way to describe it is to use the Stokes parameters, which are nothing else than Cartesian coordinates of the tip of the electric vector that is presented here for the spherical coordinates as the IP, 2psi and 2xi. So basically, it's the vector, the spherical, the Cartesian coordinates of the electric vector, and this p is the fraction of polarization, so which is from 0 to 1. So if it's 0, it's the light is unpolarized. If it's 1, the light is polarized. And sometimes the Stokes parameters are given as S0, 1, 2, 3, or as IQUV, where I is the total intensity, Q and U describes the linear polarization, and V describe the circular polarization together with its sign, if it's right-handed or left-handed, so if it's plus or minus value. And here you have the example of 100% polarized light. If the Q is polarized for 100% and U is 0 and V is 0, this is the case for Q and V 0 and U greater than 0. And this is the case for the V greater than 0 and Q and U being 0. And here you have some other examples. I encourage you to go to the Wolfram demonstration webpage, where you can very nicely play around with the Stokes parameters, as well as with some optical elements to understand quarter wave plate or half wave plate. It's very useful, especially for students and for lectures. Just a short outline of my talk. I will shortly show you the new results of Crab pulsar and its nebula in linear and circular polarization. Very shortly, we'll mention some AGN photometric monitoring and the results of the white dwarf polarimetric survey. And then at the end, I'm going to present you the NEOPOL, which is the Polish polarimeter for near-Earth objects observations, and a few words about the other polarimeters that we are either have or we will have in the future in Piwnice. As you know, We know more than 3,000 radio pulsars. Some of them, they are also visible in other domain of electromagnetic spectrum. My main interest is the optical pulsars. So the pulsars which are young and energetic, like Crab or Vela or Geminga. And as you can see here on this so-called HR diagram for pulsars, so the diagram that shows the period derivative as a function of period, where you have the classical pulsars here located in the center of this plot, and here you have the recycled pulsars, which most of them, they are in binary systems. So we are interested in the young and energetic because we hope that you can see them in optical. The problem with optical pulsar is that they are very faint objects. The Crab is the brightest, which is 16.5 magnitudes, and all the rest is much below 20. And you can also see that the rotation period of these neutron stars are very fast, so it's 0.1 seconds, which means that you need a very fast polarimeter and also very sensitive one. And additionally, you also need a big collecting area, so you also need a big mirror to collect enough photons. I think like 1 year and a half, I gave a seminar at the institute, at the observatory in Warsaw, so I'm not going to repeat it, but just shortly, we have done so far probably the best optical polarization measure of the Crab pulsar. This was performed on Nordic Optical Telescope, which is 2.5 meter telescope with the Optima instrument. It's a very fast photopolarimeter that is based on optical fibers, and the optical fibers are connected to the single avalanche photodiode. So basically what you measure time of arrival of each single photon. And the fiber bundle is organized in such way that you have a center fiber and then 6 fibers that measure the background. And on the sky, this is how it looks like. So this is the Crab nebula. The central fiber is the Crab, and then you have 6 fibers that measure the background. To measure the polarization, you also need to have the part of optical instrument that will split the polarized light in different polarization plane. So for this, we are using 2 double Wollaston prisms, and that's why you have the 4 spots of the target, and they measure different polarization planes, so 0, 90, 45, and 135. And once you have the Stokes parameters, you can plot them as it's presented here, so on so-called QU diagram, and here in color you have the light curve of the Crab, and most of you probably know that it has 2 peaks. It has main pulse and interpulse. And here you see how the tip of the electric vector is making these loops. The bigger loop represents the main pulse, whereas the smaller loop represents the interpulse. And once we have this QU calculated, then we can calculate the polarization degree, which is square root of Q squared plus U squared, and then position angle, which is half of Arcus tangens U over Q. What then? Then we can check how the position angle behaves as a rotation phase of the neutron star, and also how the polarization degree behaves. And it's presented on these panels. And just remind you, the star rotates 30 times per second. It's 2 kiloparsec away. And with the highest resolution, we can go even to 4 microseconds. So 1 dot on the most right-handed panel is, in this case here, it's 10 microseconds. So you can see that there is a big swing, changes of the position angle. And you can, on the right panels, this is the zoom around the main pulse, and you can see that the position angle was changing not only during the maximum of the optical pulse, but also at the maximum of the radio pulse. The blue line is the 0 phase for the 1.4 gigahertz radio pulse of the Crab. And also interesting enough, is that the polarization of the optical light happens not in the maximum of the optical light, but in the maximum of the radio light. However, this was done more than 10 years ago, but we are still trying to measure not only linear but also circular polarization of the optical pulsars. And for that, I contacted Sloan Viktorovich from aerospace, and he is the godfather of Polish 2 polarimeter. And his main aim is to measure the reflected light from exoplanets. So here on the panel, on the left panel, you can see the prediction for the system when you have the host star and the exoplanet on phase on orbit, which means that basically you will see no modulation as an orbital phase, whereas in case if you have transiting exoplanets, so the system which with the inclination around 90 degrees, then you would expect that there will be some modulation of the polarization light as a function of orbital phase. However, please take into account that its effect, of course, the reflected light is very tiny, and it's the effect on 10⁻⁵. So to get a decent result, you really have to have quite a lot of photon statistics. Polish 2 is a bit different instrument than Optima. It's based on photoelastic modulators. Here they are. Then we have the Wollaston prism. Then you can put the neutral density filters, because I mean sometimes you have to dim your objects. There are also some stopping lens. Then you have the place where you can input the color filters. And then you have the photomultipliers. It sounds like, you know, oh, my grandmother was using photomultipliers, but it's not. They are still in use, and they have some advantage over CCD or other types of detectors because they have very broad dynamic range. And this is wonderful because with the same instrument, you can observe either Venus or neutron stars in optical regime. And of course, for other CCDs, you will get in troubles if you observe Venus because you will saturate your detectors very soon. Of course, it also has this disadvantage because it has low quantum efficiency, but well, something for something, right? So we were performing the crop observation on 3-meter Shane telescope at Lick Observatory. And first of all, we need to really understand what is the amount of interstellar polarization, because otherwise you cannot really correctly subtract whatever you gross count. I mean, altogether, you have to really distinguish between the components coming from the interstellar polarization or if this is intrinsic to the source that you measure. So to do that, I took the Gaia DR2 and I choose the stars which are in the direction to the crab pulsars. They are plotted here on the left panel. And then I also sorted them according to the brightness, but also according to the distance, so that they will be between observer and the crab, so closer than 2 kiloparsecs. And they are marked with green colors here on this lower panel on the right. And here you can see them as bigger spots. And this star is indicated here. So these are this few pretty bright star in the vicinity of crab pulsar. So we use this Polish 2 polarimeter, and this is what we got. So on the left, you have the position angle as a function of distance of these 8 stars that were selected from Gaia. And as you can see, the closest one, which is around 50 parsecs, it has the position angle differs a bit from the rest, but it's nothing surprising because then, I mean, you don't, the contribution from the ISM is probably very small. So farther you go, then the position angle, it gets constant. And as you can see also, the color bar indicates the linear polarization degree. So, which is nothing surprising. Farther you go, higher polarization contribution from ISM you get. So we have the constant behavior of PA here in this case indicates that this is due to ISM. Going to circular polarization, this is on the left, on the right panel. Here you see the circular polarization as a function of linear polarization for the same 8 stars. This checks 2 things. First of all, you can see that the circular polarization within the errors is around 0%. And second, we don't see here crosstalk between linear and circular polarization, which happens pretty often. with color, now here in this panel, you can see that the colors indicates the distance. So basically, these four stars, of course, they are closer and these are farther, but nevertheless, the circular polarization here is 0. So for the moment, our results for the Crab nebula, not the Crab itself, is that the Crab pulsar, which is because the Polish 2 is photomultiplier, so you have a diaphragm. So the spatial resolution is defined by the diaphragm. So here is this plotted on the map of the Crab pulsar. This is the result that I'm presenting on the left. Are for the it's like total total polarized intensity measure from this region of the Crab pulsar. And here you have the Stokes parameters, and you can see that the V that represents this is representing the circular polarization is detected on almost 10 sigma level. And you can see here that linear polarization degree is almost 20%, whereas the position angle is 165. And basically this confirms our previous optimal results. And so all that you have to take into account if you want to get the polarized netto information about the Crab, especially on the circular polarization. So here they are very preliminary results from Polish 2. The polarization degree but it's still like gross, so it's not nebula and background subtracted. So here you see the QU and position angle as a function of rotation, but also what is probably here the most important, this is the modulation of the circular polarization as a rotation of a Crab pulsar. However, still we are, due to COVID last year, we decided we couldn't honestly observe more, and we are doing careful reanalysis of all the data from Polish 2, including calibration data. So I'm sure that these plots will change soon. The other project that I was involved is the RoboPol. I think you have heard about this polarimeter already. It's this polarimeter was mainly built for monitoring blazars, and it's again based on 2 Wollaston prism. So you have again each star is has 4 images, as you can see here on this close-in panel on the right. This is the whole image from the CCD camera of the RoboPol. The mask is necessary here to reduce whatever reflections on the source. So here you have each source is presented as 4 spots, and they correspond to the intensity on this intensity corresponds to different polarization plane. So again, it will be 0, 90, 45, and 135. And from that, so basically what you have to do is to get you calculate you do, let's say, normal photometry calculations, and you get the flux, and then you input this to this equation to get normalized Q and U parameters. And then here we have the equations to calculate the errors, and you will be able to get polarization degree and position angle. Recently, we publish a full data set from the RoboPol monitoring. It's more than 5 years, and there are more than 200 AGNs in this data set with 5,000 observations. For each AGN, you have, of course, the name, the Julian day, the instrumental polarization, normalized parameters, and then the net polarization parameters, normalized Q and U, and also calculated polarization degree with error, and electric vector polarization position angle also with error. And there will be 2 more papers coming from this data regarding the statistics and the behavior of the position angle of the electric vector during the time when the Fermi, for example, was observing the flaring activity in blazars. So we have two samples. One was this gamma ray loud sample, and the other was the control sample, and they were based on the photon flux cut from the Fermi 2 second and the third catalog, as well as, of course, on the optical brightness, while the RoboPol is mounted on 1.3 meter telescope in Crete, in Skinekas Observatory on Crete. So you can, I mean, if you want, you can download all this data. They are already available in archive. So a byproduct of this 5 years of monitoring was the monitoring of polarization standards. And whenever you want to work with polarimetry, this is really, well, how to put it, kind of nightmare, because many of these polarization standards, they're very bright stars. So if you go to the bigger mirror and to more sensitive detectors, of course, you will saturate them very quickly, and it's pretty problematic. So during this 5 years of observation of blazars, they also monitor polarization standards. Here is the list of the so-called high polarization standards. And on the right-hand side, you can see the difference between measure RoboPol position angle versus the catalog value. And you can see that the error is on the level of 1 degree. And you can also, one of the most interesting results from that paper is that we see that the stars that were previously for many years, for like 30, 40 years, used as polarization standards, they cannot be anymore used as standards while they are variable. They also, you have to not only observe the high polarization standards, but also the zero polarization standards. Zero polarization would mean that you don't expect that the polarization degree should be 0. To get it, then you expect that your Q and U value of the Stokes parameters, they have to be 0 or very close to 0. Otherwise, if it's another value, this means that you have polarization, instrumental polarization. And here you have, these are the zero polarization standard observed over this 5 years period with RoboPol. And you can see that the black cross shows the average of the all polarization, and you can get that the average instrumental polarization in case of RoboPol was 0.15. And basically it was pretty stable, and it's something that you have to, this kind of observation you have to perform all the time whenever you are using your polarimeter to check the stability of your instrumental system. It was also so the other project that I'm the PI is survey of continuum polarization of white dwarfs in R band. We were the aim were there were two aims. First was to look for the good candidates for fainter standards, as I described the problems before. And second, to check if there is any dependence on the white dwarf spectral type and the polarization, linear polarization features. It has never been done before, so we are working on this project since 2014, and we already have quite a number of data. Just to remind you, the basic description of the spectral type for the white dwarfs. 80% of white dwarfs, they are DA type, which means that the atmosphere is hydrogen rich. So you see the hydrogen lines in their spectrum. The other 20%, they are DB types, DB white dwarfs. So the white dwarfs that they have the helium lines. However, they don't have any hydrogen lines. And then the rest is just, you know, a few percent of other types, having metals, for example, or ionized helium. There's other also type of white dwarfs, which are called DC white dwarfs. And here you can see the example of the spectrum for the DC white dwarf. Well, basically, you don't identify any lines in their spectrum. So our because they don't show any lines, so you also cannot use the Zeeman effect to measure their magnetic field value. Therefore, we started to conduct this project on broadband polarimetry, linear polarimetry for DA, DB, and DC white dwarfs. And here you have HR diagram for white dwarfs, let's say corner, and with different types indicated by different colors. So you can already see that, for example, DB white dwarfs locates here on the left upper corner of the white dwarf family, let's say. So these are results from already from 2014 and 16. We already had an indication that indeed there is the difference in the linear polarization of different spectral type of white dwarfs. And here are the results from 2019, and you can see that first of all we were trying to increase statistics for DB and DC, but as I mentioned, I mean 80% of white dwarfs are DA, so of course it's much harder to find DB and DC type white dwarfs. And you can already see here the histograms with the polarization degree for different type. So DB, on average, they have 0.6 linear polarization degree, whereas DC, they show much stronger polarization. And if you gather together all the data from 14, 16, 19, and the data from 2020 are not included yet here, you can see that DA white dwarfs, they have, here are the histograms, and colors indicates different spectral type of white dwarfs. DA, well, the same is, and maybe easier to read, is represented on the right upper panel, where you have polarization degree shown as box plot. So you have the average polarization degree for the white dwarf of DA type, all of them, of course, isolated. DA, DB, and DC. And you see that DC white dwarfs, they show on average much higher polarization degree. And this is mainly due to cyclotron radiation, but in the strong magnetic field. So if this DC type white dwarfs show already higher polarization degree, this means that their magnetic field must be stronger than 10 to 8. Otherwise, they would show the polarization degree, but in the infrared regime. Interesting enough is also that if you go to the binary systems, where at least one component is a white dwarf, you can see also that for example, there is difference between average polarization between systems where you have DA plus DM system in comparison, for example, to DB binary system. So based on DB white dwarfs. This data will be updated with 2020 data, where we have more than 30 or 40 more measurements of white dwarfs, and probably we will even strongly, the statistic will increase, therefore we will be able to have a stronger conclusion on that dependence of polarization degree versus spectral type. I know that all my Polish colleagues, they know Piwnice, but maybe for your postdocs or foreigners that they have never been here, I'm just showing the Google Earth screenshot. So Piwnice are located 10 kilometers north from Torun. We have the radio observatory part, which is 32 and 15 meters dishes. And then here is the optical part, where we have 4 domes, where 3 of them, they are still in operation. The third dome is hosting the famous Draper telescope. So I'm very proud that we were able, even apart from, I mean, having this pandemic, we were able to renovate and paint this radio telescope, which can also measure the polarization, however, in the radio domain. And it's one of the stations for the VLBI network. Going back to optical part, we have 90 centimeter Schmidt-Cassegrain telescope, where we introduced 2 Savart plates. Savart plates are the bifringing material that will split the incoming beam for the ordinary and extraordinary ray. So they will have the polarization plane will be 0 and 90 degrees. if you use the second Savart plate, but you will rotate by 45 degrees one to the other, then you will measure 45 and 135. So by doing this is really one of the simplest way of measuring optical polarization. And the advantage of this is that at least at once you are getting one of the Q parameter, right? Because the 0, 90 will measure you the Q, and 45, 135 will measure U. And again, using, so you calculate the fluxes, you get the Stokes parameters, then you can calculate the polarization degree. And here is an example of the standard, which is not standard anymore, but I like this, the star, because it's very highly polarized. For optical polarization, something on the level of 8%, it's considered to be high. So you can see that already these are preliminary results, a wide band. So you can already see that we can do decent polarization measurements with this Cassegrain-Schmidt 90 centimeter telescope. This is how the camera, sorry, I didn't mention. The camera is in the primary focus, and we have the filter wheel where we put the Savart, and in front we can put one color filter, which is something that needs to be upgraded, because otherwise you cannot do multi-wavelength polarimetry. So these are the Savart plates themselves. Physically, they have a size of 2 centimeter by 2, whereas the filter wheel spots, they are like 2 inches. So that's why you, on the field of view, you see these black corners here. And this is the example of the whole image from this SB camera. This is high polarization standards, 10 magnitudes, exposure time 30 seconds, and the field of view is 35 by 35 arc minutes, and the pixel scale is 1 arc second per pixel. In the second dome, we recently get back the mount that was in Lubomir for some time. This is pretty decent mount. This is GM4000 from a 10 micron company. And for the moment, we have now just 8 inches mid telescope with the SB camera, but we are going to upgrade this to 50 or 60 centimeter telescope even this year, maybe within the few next months. We also bought new camera from Moravian Instruments, G4, 2 CMOS cameras. One will go to this Schmidt Cassegrain telescope, and one will go to the second dome. And our idea is to measure very simple, but even better than just, you know, this simple Savart by Savart polarimeter. This polarimeter will be similar to this Denver University small telescope polarimeter, which is called DustPol. And so you have, they have exactly the same mid, by the way. And you can put here the filter wheel. And the clue of this polarimeter is that you will have rotating half-wave plate in front of non-rotating Savart plate. So the image will look like this. And then by rotating the half-wave plate, you will rotate the polarization plane. Therefore, you will be able to, again, get the Stokes parameters. And in this case, it will be even, probably we will get much better accuracy, because you can use different orientation of the half-wave plate. And then you can use this very nice general case for N polarizer description of all the equation for the Q and U and V given by Sparks and Axon. The great advantage of this small instrument will be that you can have color filter in front, and we can optimize this in 2 ways. We can optimize for the blue and red part, so it can be UBV or VRI, and moreover, if you change the half-wave plate to quarter-wave plate, you will be able to measure not only the linear polarization but also the circular polarization. So in principle, I hope that this year we will be able to measure linear and circular through VBR and I. Why? Because as you might have heard, there is something like which is called Slowikowski polarization law. It's empiric equation for the ISM polarization, and this is basically how the polarization behaves as a function of wavelength and the polarization, the interstellar polarization. So you can see that the polarization changes as a function of wavelength, whereas the position angle is constant. And this is exactly the case, remember, for the Crab pulsar, when I was showing you that the stars in front of the Crab, they show only interstellar polarization. So we can easily get the Q and U values for the interstellar polarization in front of Crab. So on the left-hand side, you have the interstellar polarization and the Cherkovsky law, whereas on the right, you have the BD31, which is the case, which is the stars that exhibit some circumstellar disk. And you can see that the polarization degree for in blue part up to let's say 700 nanometers is flat, and then it's even getting higher. So this shows that there is still a lot of very small, tiny grains that scatter a lot the blue light. Therefore, you have much higher contribution to the polarization degree from that scatter light. And you also see that that there is big changes in the position angle as a function of wavelength. Therefore, the multi-wavelength polarimetry is a very useful tool to disentangle between the ISM polarization and intrinsic polarization to the target. So this was the first, second. In the third dome, we have the Draper. And in the fourth dome, we have the same telescope as you have in Ostrovik. So the 60 centimeter Cassegrain telescope. So I'm sure, and the Suchora, they have the same. And again, on Suchora, they have the camera in the primary focus. And you can see we again used the two Savart plates for the observing campaign to observe the OJ287, the Blazer, last year. Przepraszam. And here you have the pixel scale and the field of view. I don't remember. I think this is one of this is the Blazer in the middle. And we also observe the standards. And even with such a simple technique, you can really get decent results, because in black, these are the polarization standards. In black, I gave the numbers from the literature, whereas in the red, you have the numbers that we obtain from the Suchora data. And you can see that we are, the accuracy of the polarization degree is 0.1%, whereas for the position angle, it's a few degrees. And we were performing observation of OJ287. Here you see one of the observation taken in March last year. And you have, because of course we were using, you need to use two Savarts in sequence, right? First two, and so on. So you have two Savarts multiplied by 14 by 120 seconds. So you have, and this is the results for the OJ287 one day, and this is the position angle with the error below 1 degree. In the fourth dome, we have the 60 centimeter Cassegrain telescope. And now, since a few months, we are, I'm involved in developing of NEOPOL, which is the Polish polarimeter for near-Earth objects observations. PI of this project is Agnieszka from Sibylla Technology. Here are listed people that are involved. I'm sure that some of the names are known to you. And this is the project that is under, basically we were going, I mean, that our aim was to design, build and test the polarimeter for ESA. And it will be, the destination telescope is this 1 meter OGS, so optical ground station for ESA on Tenerife. However, due to COVID, of course, everything was a bit postponed, and this polarimeter is still in Piwnicy, and we are testing this polarimeter. So what do we want to observe is the scatter light from the asteroids as a function of phase angle, and the phase angle is the angle between the Sun, the asteroid, and the Earth. And of course, it's, I mean, there are many asteroids already known, and for many of them, the polarization is measured. So here you have the polarization curve. as in one of the example. And this equation is again an empirical equation that describes this different polarization curve. So the dependence between the polarization degree and the phase angle. Moreover, the shape, as you can see here on different cases, depends very strongly on the albedo, so on the composition of the asteroid. So depending on the class of asteroid, what is the porosity of the asteroid and what is its albedo, you will be able to distinguish to which class of, based on polarimetric observation, you are able to distinguish the class to which the given asteroid belongs. So this is the aim, where we want that we want to reach. And here a few technical details on this polarimeter. So you have the collimating lens. Here is the filter wheel where we have 5 slots. Then this is the double Wollaston prism. And then the beam is then focused by the lenses on the detector. In this case, this is FLI camera. In front of the polarimeter on entrance, we have the slit that will protect us from any overlapping sources, and also so we will have the slit on the sky. It will be very tiny field of view, which is the kind of disadvantage of this kind of polarimeters. But on the other hand, at the same time, you can measure all 4 intensities. So all 3 stocks IQU. These are the hardware parts for this NEOPOL. It was assembled by Staszek Kozłowski. Here is the double Wollaston. Here is the slit that is at the entrance of the polarimeter, and this is how it looks like after it was assembled. And also we have the small PC here that controls the filter wheel, the camera, as well as we have some sensors that measure the humidity, temperature, and other parameters of the polarimeter, so we can control the conditions. Before going to the telescope, of course, we have to prove that this new built polarimeter is working. And for that, we took the NEOPOL to the lab in the Department of Physics, Astronomy, and Informatics at our university. Dr. Piotr Kolenderski was kind enough to let us in to his single photon applications laboratory. Here is the optical bench, and we were using a Savart laser, which is a very stable laser, of course, with the optical fibers. On this plot, we are just checking the quality of the fibers, if there are not any scratches at the entrance. And this is the polarimeter, and this is the optical test system. So here you have the optical fiber, and then the next is the neutral density filter. Then we have the lens, the beam splitters. The beam splitter, because the light going out from the laser, it's 100% elliptically polarized, but we want to test the linear polarization, so we need to have the beam splitter, and the light passing the beam splitter will be 100% linear polarized, perpendicular to the optical bench. And the next element is the rotating half-wave plate, and then we have the lens, and then we have the entrance window to polarimeter. So this is which is here, and then as you have seen, there is collimating lens, filter wheel with color filters, and then we have the Wollaston, the lenses, and then the detector, so the FLI camera. So because we have here this half-wave plate, and we will rotate this half-wave plate, with the rotation, what you would expect is that you will get two beams that one beam will vanish and one beam will get the intensity, will increase its intensity as a function of rotation of the half-wave plate. So basically, in absolutely ideal case, both of the light curves that we measure here for the upper and lower spot should be a sine function. This is the zoom of one of the spot, and you can see that there is a lot of diffraction pattern, and also the profile. Well, it's far from being really nice Gaussian profile, but we couldn't really fight against these problems. And this is mainly caused probably by the fact that the optics were not perfectly aligned. And also we have some reflections. If you going back to the lab data, you can see here are the raw measurements, and on the upper panel you see the sine function for the upper spot, and the second panel shows the lower spot. And then on the third panel, both fitted sine function are shown, and the red line indicates the sum of them. Because of course, I mean, as you can imagine, by rotating the half-wave plate, you don't change total intensity of both spots, right? The sum should be exactly 100% polarized, and this is the sum on the lower panel. You see the sum of these two spots, and you can see that indeed we are, as a function of rotation, maybe the half-wave plate itself in the frame was already tilted a bit, and this can cause the loss of the partial loss of the polarization degree. But as you can see, we are not doing that bad. Of course, in the ideal case, it should be just straight line on the level of 100%. Here we have some modulation on the level of a few percent, from 94 to 100%. But we were taking into account all the circumstances with COVID, we were pretty happy, and we went to the observatory. We mounted this on the telescope. This is our 60-centimeter telescope in the fourth dome in Piwnice. This is the NEOPOL. Of course, as I mentioned, the field of view is very small, so to orient yourself, and we still point the telescope manually, so you better need a finder to orient yourself on the sky. And these are the images from the finder on the left. So here you have the field of view, and the red color marks the field of view for the NEOPOL. And on the right, you see the image from the scientific image from NEOPOL. This is one of the standards. So you have, right, you have 4 stripes, because you have the two Wollaston's. They split the light for 0, 90, 45, and 135. But you can see that the field of view is pretty small. It's let's say 15 by 1 arc minute. And why is it problematic? Because you can end up where you have only one star in the field of view, as here, for example, this is one of zero pole standards. And this is in arc filter, the exposure time is 10 seconds. But here, of course, on one star, you will be not able to do any astrometry. So not having the finder will be really difficult to identify yourself in the field of view. On the right-hand side, you have an example of the flat field. And as you know, the morning and evening sky is very highly polarized, which is already seen, which you can already see here in this image. And you see that we have to, due to the fact that each stripe is has different level of intensity, you have to take into account that you need to really cut stripe by stripe to perform proper photometric analysis and to get the proper master flats for each single stripe. Okay, I will finish soon. During summer, I was here in Piwnice performing the calibration of this polarimeter. Here you have the list of unpolarized and polarized standards, together with the values of polarization degree and position angle. We also observe few debris disks, and from our results, I can say that polarization accuracy is on the level of 0.1, whereas the position angle is a few degrees, and the instrumental polarization is of 0.5%. When Łukasz invited me for seminar, I told him, let's do it in February, because then I will have nice data to show. Unfortunately, due to the weather, I couldn't open the telescope at all in October, where we have very nice NEO. These are ephemeris for Piwnice, of course. And in October, there was pretty decent and bright, I mean, taking into account our 60-centimeter mirror, NEO with this 159402. And you could see that it was even brighter than 30 magnitudes. So all the time I was in Piwnice hoping to catch it and to present today some of our first near 8 objects polarimetric data, but unfortunately I cannot, and I'm very sorry to disappoint you at this moment. If you want to read some more on polarization, we have, I think, nice proceedings from the European Week of Astronomy, and it's basically about the polarization from infrared to gamma rays. And if you have any questions, please contact me, and I will be happy to collaborate on any polarimetric projects that we can conduct here. Thank you.
Okay, thank you very much, Agnieszka. I'll do the virtual clapping and real clapping on behalf of everyone. Questions, please. There is a question from Paweł, please.
Yes, hello, thanks Aga for this presentation and very nice overview of your activity. I am interested in collaborating in this matter with you, as you know already, but I have a question regarding one slide you have presented some results from 60 centimeters, this one, 27th.
For OJ?
No, before, one before.
Okay.
These are the results from the 60.
From Suchora. This is from
Suchora, right? Okay,
yeah.
because I missed this.
No, sorry. It was.
I thought that was from like, Savart plate.
It's the same case. I mean, basically, in any of these telescopes, we could put the Savart and perform such an observation. They have nice idea to put it in the primary focus. So, and we have like long cadence here. So these observations, one day I hope that Staszek Zała will, with whom I'm collaborating on this project, he will publish this data. But we have pretty long cadence, and this polarization standards, they are, I think I can have, this polarization standards, they are taken, we have, more than 1 year of observation. So we check that the stability of the system, I should say this.
I think up until now, it's something around 4 years of observations of OJ.
I think I was analyzing the data after, first of all, after aluminization of the mirror, because they did it like 2 years ago or 1.5 years. So for sure, I didn't take the data that were collected before.
Yeah. And what is interesting here, that the error of the polarization degree is on the order of 0.1, 0.2, let's say.
Yeah, it's pretty decent.
Yeah, so this is for the Savart plates. This is really nice because the method is simple and the instrument is very simple.
Yeah.
So even at Polish weather conditions, it is possible to get really nice precision. But what is worth to mention, that with the new polarimeter, which you are going to build in Piwnice,
This one.
this precision, yeah, the small one, also with Savart plates, but the precision should be even better, below 0.1%, and this is the aim, right?
Absolutely, because it's like if you use this different orientation of the half-wave plate or quarter, whatever you want to measure, you will over-describe the equation, right? You have three unknown, IQU, but you will have many measurements. So which this should for sure help to decrease or increase the accuracy, right?
Yeah, that's right. Yeah. So this will be really helpful from the practical point of view, because then you can observe many different targets, not only blazars, AGNs, and really highly polarized objects, but also some small polarized or low polarized.
Yes, and
targets.
I think that within this week I will know if I have money for 50-centimeter telescope that we can put here exactly in this dome on this mount, which would be, of course, much better than the small one. However, you want to observe bright targets, so, right?
Sure. Yes. Okay. Thanks.
So yeah.
Any more questions to Aga? I have one regarding the magnitude limits. What is how much flux do you need to measure something in magnitudes?
Okay, I mean, read the first. So of course, it's to get the statistics. You really need a lot of photons, depending on really to which level of accuracy you want to go, right? But for example, this. I don't have such a plot yet, but I should really prepare them. So the brightness of the brightness, no, the error as a function of the brightness. But for example, this standard, it's 12.5, and we can get 0.3 polarization degree. One has to remember that it really depends on your which kind of physics you want to learn from that. Because, for example, with Savart, you will never, in this configuration, you will never measure simultaneously both parameters, right? So if you are looking for very high time variation sources in short cadence, then this technique will not apply. You can use NEOPOL for that. Or even faster polarimeters, but you have to, if you want to check variability on short time scales, you need to measure both Stokes parameters at the same time, right?
Okay, I have actually more questions and discussion, but we can move it to later. I don't see any more questions, so I will thank Aga on behalf of everyone here. Thank you, Agnieszka. And I would like to invite everyone who wants to stay a few minutes after the official stop of the streaming and recording to online, offline talkings, the discussions with the speaker. So I thank everyone. This was the last seminar, I remind you, and the first seminar will begin with the beginning of the term, which the date I have to check. So I will not tell you. So happy exams for students and happy break for everyone else. And I'll see you in about a month at the seminars. Thank you. Goodbye.
Thank you.
Bye.